Hello everyone, today we are going to be going over the Blind 75 in C++, and today we're working with implement trie. Now, before we get started for the entire thing, we're not necessarily working with the input, output, what data structure / algorithm to use, and then our output questions. What we are really focusing on is filling out the whole data structure for the trie and working out how to, what to do with exactly all three functions to be able to replicate the trie. For whenever going to question, a trie, pronounces trie, or prefix tree, is a tree data structure used to efficiently store and retrieve keys in a data set of strings. There are various applications of this data structure, such as autocomplete and spell checker. And so, I can, however, showcase a few things. Let me just get the comments inside for each part for our solution. So a trie, need to initialize the trie object, insert, and our insert function is supposed to insert the string word into the trie that we have, and the search is going to retrieve true if the string word is in the trie, if the word is in the trie, and then starts with is going to return true if there's a previously inserted string that has a prefix. So, like, we're asking ourselves, is there something that starts with XYZ? Pretty straightforward over what to do, and so what I'll be doing is just going over the steps over what to do to be able to solve this problem, so that way you folks can be able to apply this on your own time. So actually, I'm going to go over to the very first part of what we need. So this part is going to be for step 1. We're actually going to create a trie node for the characters of a given string. One of the constraints, luckily, is that word and prefix consist only lowercase English letters, and there are 26 characters in the alphabet, the English alphabet. And so I'm going to showcase the steps of what we need to do. This entirely would be step 2. Yeah, step 3, step 4, and then step 5. So going about each one, and I'm going to put all the necessary steps that we need to help break down exactly how to solve this problem. So, focusing on exactly how to solve the following problem, what we need to do is that for our following steps, for step 1 entirely, A, B, C, D, E, is that we're going to create our trie node structure. That what we'll do is that first thing is that we will, actually I'm just going to put this all in Roman numeral for clarity. So first part, we're going to declare an array to hold children nodes. Next part, we're going to declare a Boolean variable to signify there is a word. Third, we're going to define the constructor for trie node, and then we're going to initialize all children nodes to null, and then we're going to initialize is word to false to start things off. So the way we're going to go about step 1 is that we are going to create a class called trie node, which will be public, and then we'll have 1, 2, 3, 4, 5, and actually this is going to be important. So 4 and 5 are inside of a constructor. So the first part that we're going to have is that we're going to initialize all the characters. children to be 26. And then the next part is that we are going to initialize isWord. So this is how we create our constructor, where form 5 are going to be inside of it, to determine exactly, hey, we accounted for the character and determining if there is a word. So for int I is going to be equal to 0, I is less than 26, and then I is incremented as a typical for loop, and then children I is going to equal null. Then we're setting isWord to false. You can do the same up here, going isWord and set it to false. I'm just putting it in for the sake of clarity between, hey, we have this, and then we're also setting it to false as well. Just saying, hey, this is how we create our boolean, and then we can set it to false. Now for the next part that we will do is that we will now declare the root node of the trie and then initialize the root with a new trie node. So this part only contains 2 steps that we need to do. Lies the root of the trie node, and then set the root to be the new trie node. So the way we go about this is going to be looking like this, strangely enough. So I'm just going to move this up here for further clarity. And that trie node for our root. And then inside of the object, this will be for step 2. Step 1. Root is equal to new trie node to initialize. There we go. As such. Now, for step 3, we're going to work on our insert function. We will declare the node to be the root, scan every character from our given word. If the node for the following character has not been inserted, we return false. We put in a new trie node. Then we set the node to the next child node. Then declare that we have inserted a word in the trie structure. Step 1, 2, 3, 4, 5, the way it's going to look. It's going to look like this. Yeah, I'm just going to clean up all this as well. Three 3.1, 2, 3.3, 3.4, 3.5. So for inserting, trie node, root, and then we're going to scan for character, word, and then we're going to have 3 and 4 on the inside, and then since we're determining if the character has been inserted, so if the node of the children character. This is how we just put up for each character. And then we'll have new child. New try node. And then the way it's going to look, so we have node equal to node children for 4, C, A. Mind you, we're dealing with characters, so we have to format it this way. And then finally, we're going to declare that isWord is going to be true. So we do that. Now working on search. What we'll do for our steps is that create a new instant. We will declare the node to be the root. Then we will scan every character from our given word whenever we call upon this function. And then, if the character is not in the try from our root, we return false for isWord. Then set the node to scan for the next character on word. Number step 5 in this. If we have reached the end of the word, we will return true. But overall, the isWord value. So the way it's going to look like for search, it's going to be for the following: 4.1, 4.2, 4.3, 4.5. The way it will look, we have try node equal to root to search. Then we are going to scan. All right, hang on, 4.5. So char reach word. We're checking to see if the character is on the inside. So if node for children C A, we will return false. Then 4.4, we'll have the node move on for the next one. So literally, it'll be this. And finally, we will return the value. Return node isWord and move along. And finally, with the starts with, what we will do is that you can get, okay. Is that for 1? What we will do is that we're going to do the same thing that we did before. We're going to scan for every character of the word. Given the fact that we're looking for a prefix. In mind inside the parameter. There we go, that's more like it. So we will scan every character from our given prefix. Then If the character is not in the tree from our root, we return false. Since we're just focusing on the Boolean right here if it starts. And the reason why that we said is word is that for the end, and this just indicates false given the fact that we have a Boolean right here. So just for further clarity. And for the fourth part, we will redeclare as up here and scan no. Then set the node to the next character onward. Then finally return true, assuming there is a prefix since we scanned for every single character. So similar to the other two following functions at the top, we're just dealing with this. So we're going to do with 5.1. 5.2, 5.3, 5.4, 5.5. First part, try node root 524 character prefix. Have the 2 as required if the node A will return false. Otherwise, in this case, we'll just keep going onward while scanning for every single character. Node children C A and return true. Okay, let's just double check to see if we have everything already set in place. Yes, yes. We've already did that. Try node is the root. We created our instance of try node. We've created isWord, onward. Okay, let's see. Let's double check. All right, there is a semicolon error. Don't forget that. And don't forget that. All right, passes all the test cases. Let's submit. All right, now just to give a rundown and breakdown of our space and time complexity for the following solution is that our time complexity for both inserting and, well, we are going to have it for every single different following function. Let me just, I'm going to, there we go. Let me clean this up and then also showcase to you folks what the full program looks like. Okay, now, just to give a full breakdown on our space and time complexity for our following solution is that the time complexity for both inserting a word and performing a search overall is going to be O of M, where M is referring to the length of the word or prefix being inserted / searched. And our space complexity is going, for the whole try, is going to be O of N, where N is the total number of nodes in the try. In the worst case, if we insert lowercase English words only, we would need a maximum of 26 nodes for each level in the try. And so, yes, this was implement a try, or create a prefix tree. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put in the comment section. And as always, take care. Cheers. Bye-bye.